Okay, so doing number 8 here. Um, so drawing our domain, we've got a paraboloid, and then there's another paraboloid sitting on top of that. This is kind of what our domain looks like, right? Okay. So over this domain, we want to compute triple integral of, let's see, what was our domain, our thing again? Oh yeah. So it's r squared dv. Did we say delta equals 1 again? Yeah. Okay. Good. Right, so what is r? Well, now we're rotating around some line. We got this wacky line where x is 3 and z is 5, and that's, some line up here, parallel to the y-axis. Right? It's parallel to the y-axis like that. So I've got to figure out now a formula for if I've got some point x, y, z, I need to know what is this distance, the sort of perpendicular distance up here to this line. And the way I'm going to do that is I'm going to write down exactly what this point is that's closest. So that, what's the point I'm computing the distance to? And the thing is, it's got the exact same y coordinate as this point because it's a perpendicular distance like that, right? Is everybody okay with that? And what do I know about x and z? Well, let's see, x is 3 and z is 5. That was what we know about the line. Is that cool? Yeah. So that means that this distance here, that r, is the square root of x minus 3 squared plus z minus 5 squared. So when we have integral r squared dv, here's your r. R squared is just this little polynomial on the inside here. So I just have triple integral x minus 3 squared plus z minus 5 squared dv. Okay, everybody happy? You okay?
Yeah.
Okay. Okay, yeah. Okay. So now we got to figure out how to compute this integral. Remember, most of the problem in computing integrals is figuring out how am I going to rewrite the domain, how am I going to break it down. And so we've got this weird shape here. You could think about cross sections. I mean, one thing I'm pretty sure of is I don't want to first, on the outside slice perpendicular to the z-axis because there's an edge that I'd slice through, and that would mess things up. And let's not do that. Here's another tip-off. Both of these surfaces are given with, z equals, and then functions of x and y. So sure hope that when I write this thing down as a nested integral, that z needs to be solved for in terms of x and y, because I'm all over that, right? We got that's just given that z is functions of x and y. So that suggests that the dz should be, in fact, on the inside. Okay. So I pose that we ought to consider doing dz, dx, dy, for example, something like that, with dz there on the inside. Okay, so what are the bounds on x and y? Well, when I'm interested in finding the bounds on x and y, I can look at my shape and ask, well, let's just look at the projection down into the xy plane. And that projection in the xy plane is just a circle down here. Right? Now, so the range of values of x and y over the solid is the same as the range of values of x and y over its shadow. Everybody comfortable with that? Okay. So, well, that shadow is easy. That's just a circle. In fact, it's a circle. Well, I got to set these two z's, in the statement of the problem. I got to set these two z's equal to each other, but I claim it ends up being that the radius of that thing is 1. No big deal. So that means that y goes from -1 to 1, and then x goes from negative square root of 1 minus y squared to positive square root of 1 minus y squared. Oh, sorry. There we go. Is that cool? And then what's the range of values for z? Well, z for a given down here for some point, for some x and y, z is going to go from the bottom surface up to the top surface. I've already got, I can't remember to, for any given value of x and y, z goes from the bottom surface up to the top surface, and on both of those surfaces I've already solved for z. It's given in the statement of the problem. So the lower bound for z is going to be x squared plus y squared, and the upper bound for z is 2 minus x squared plus y squared. And then again, this integrand was, x minus 3 squared plus z minus 5 squared. So polynomial, integral with respect to z, plug in polynomials. This is just going to be a great big polynomial. And then, yeah, sure, we have square roots here, but trig substitutions will let you work those integrals out. So again, more Math 32. Unavoidable. You can't get away from it. Yeah. Okay. Is that all good?
No.
Okay. All right, I'm going to stop the recording on this problem. Okay.